Okay, so next we're going to revisit the so-called fundamental theorem of invertible matrices, which the previous version of which is exactly what you see in front of you that we covered in section 1.5, although you'll remember that there were a few blanks that we filled in the videos for section 1.5. But once you fill in the blanks, this is essentially what you see. And you might wonder, well, why am I showing it to you again? Well, we're actually going to add to it. And I just want to remind you what a statement like this means, or a theorem like this means. The following statements are equivalent. When you see a theorem like that in mathematics, what you're really saying, what the theorem is saying, is that all of these statements are either all true or all false for any given n by n matrix A. So if you have a square matrix A, and one of these statements is true for that matrix A, that means the other three statements are automatically true as well. On the other hand, if you know that one of these statements is false for your matrix A, then that means the other three statements are automatically false as well. So theorems like this are powerful because they allow you to switch points of views. And essentially, the more statements you have, the more options you have to switch your point of view. Okay, so that's when I said we're going to add to it. But let's just remind ourselves what these four statements are saying. So the four statements are if you have a fixed square matrix in the background, so that's what it means to be n by n. The first statement is that A is invertible. The second statement is that the associated homogeneous system, that's what this really represents, that has a coefficient matrix of A, has only the trivial solution. Remember that homogeneous systems always have at least the trivial solution. But what this theorem is saying, in particular what the second statement is saying, is that if A is invertible, the associated homogeneous system is going to have only the trivial solution. Okay, the third statement is that the reduced row echelon form of the matrix A is the identity matrix. So that's another thing that's true about invertible matrices. So if your matrix A is invertible, its reduced row echelon form is guaranteed to be the identity. If the matrix A is not invertible, well then the reduced row echelon form of that matrix is not going to be the identity. So number 3 is a useful statement as well. We actually took advantage of that, as well as the fourth statement when we developed the inversion algorithm. And of course the fourth statement is that the matrix A is a product of elementary matrices. So if A is not invertible, then it's not going to be a product of elementary matrices. But if it is invertible, then it is. That's really what we're saying here when we write these four statements down and say that they're equivalent. So we're actually going to add 2 more statements. So the fifth statement we'll add is that if I write down a matrix equation with coefficient matrix A and constant matrix anything at all. So in other words, I'm just going to write AX equals B. So I'm not going to make any restrictions on what this constant matrix is. Remember, this is the column matrix consisting of all the column terms of the underlying homogeneous system. Okay, so this is a matrix equation, and the statement is going to say that this is guaranteed to have at least one solution, no matter what you choose to be your constant column. So another way to word that is just to say that this matrix equation is consistent for any choice of constant column B. So let's say for any n by 1 matrix B. Okay, so that's the fifth statement. And the sixth statement is actually also going to be about the same matrix equation. And again, I'm not going to make any restriction on the constant term, or on the constant column. The only thing that we know for sure about this matrix equation is that the coefficient matrix is whatever matrix we have A in the background that all of these 6 statements are applying to. So what is the statement? That matrix equation has a unique solution for any choice of constant matrix. So again, for any n by 1 matrix B. Okay, and one more comment before we move on. You may notice that the 6th statement at the bottom is stronger than the 5th statement. Because if a matrix equation has a unique solution, well, that means it has at least one solution automatically. But it's just you're being more specific by saying it has a unique solution. So if you know that statement number 6 is true, it's automatic that statement 5 is true. Because remember, to be consistent, that just means you have at least one solution. Okay, so that's what you should notice at this point, that the 5th statement is a weaker statement than the 6th statement. And it's natural to wonder at this stage, well, what is the point of having the fifth statement then, if the sixth statement is so much stronger, right? It's a more specific statement. Why don't we just get rid of the fifth statement if it's giving us less information? Well, the answer to that question lies within the fact that you have to look at the perspective of someone who's trying to use a theorem like this. Remember, you might not know if all of these statements are true or if all of these statements are false, but you might be trying to demonstrate that they're all true, in which case it's a lot easier to verify the fifth statement than it is to verify the sixth statement, because the fifth statement is weaker. If you're trying to verify the fifth statement, you would just need to rule out the possibility that this matrix equation doesn't have any solutions at all. But if you're trying to verify the sixth statement, you'd have to actually specifically show that the matrix equation has a unique solution, and it doesn't involve any parameters in its solution. So if you're looking at this from the perspective of trying to prove that all of these statements are true, you would be at an advantage to be working with trying to demonstrate that statement 5 is true. But if you're looking at this from the perspective of trying to show that all of the statements are false, well, then you only need to show one of them is false. So in which case it would be easier to show that statement 6 is false than it is to show that statement 5 is false. That's one reason, at least, why you would want to include the fifth statement. Just from the perspective of if you had to verify one of these statements, it's easier to show a weaker statement. So once you show the fifth statement, the fact that this theorem says all these statements are equivalent, as soon as you verify the fifth statement, you automatically know that the sixth statement is true also. So you get a little bit of extra information for free. So that's why you might want to include statements, even if they seem weaker than other statements in a list like this. The main reason is because we're saying all of these following statements are equivalent. If this was simply just a list of properties of invertible matrices, then it would be redundant to include the fifth one. But the fact that they're all equivalent is what makes it important to include the fifth one, and what makes the fifth statement so valuable. Okay, so an application of this theorem will be the following result. So here's a theorem. I label it as application instead of theorem because I want to make it clear that we're going to use the work above to prove this. But here's what it says. If you have two square matrices, which of course it doesn't say it, but they would have to be of the same size if you're going to be able to make sense of the product over here. But if you have two square matrices, A and B, and you know that their product, when you multiply A and B, you get this product AB. If you know in advance that it's invertible, then it turns out you automatically know that both of the factors, A and B, are invertible. Okay, so that's what this is claiming. Okay, well, how do we show something like this? Well, let's just start by assuming, so suppose that A and B are square matrices such that AB is invertible. This is how you prove statements that are of the form that have an implication and a conclusion. So a hypothesis and a conclusion. The hypothesis is that A and B are square matrices such that the product is invertible. The conclusion is that both of the factors A and B are invertible. So this conclusion here, that's what we're going to have to show. But we're going to start by making the assumption that the hypothesis, the first part of the statement, which is exactly what we wrote down, is true. So that's why I started with the word suppose. So we're going to assume that, and now we're going to show that both A and B are invertible. And based on this theorem, there's 6 different ways to show that a matrix is invertible. You can show any of these 6 statements is true, and as soon as you can verify one of these 6 statements, you automatically know that they're all true. And one of the statements is that the matrix is invertible. So we're going to apply this to the matrix B first. I want to show that the matrix B is invertible, and then afterwards I'll show that the matrix A is invertible. So to show that the matrix B is invertible, it would be enough to show that the corresponding homogeneous system has only the trivial solution by the equivalence of the first 2 statements here in this list. So that's how we're going to start. Suppose we got a solution, which I'll label it as x bar with a 0 as a subscript. Suppose this is a solution to the homogeneous system which is associated with the matrix B. So in other words, assume that it's a solution to that system. Well, my claim, and I'll even write claim just to make it clear. I haven't demonstrated this yet. I'm going to demonstrate it to you right after. My claim is that x bar naught is also a solution to this matrix equation, which is really the homogeneous system associated with the matrix over here, this product, AB. Okay, and that's going to be powerful once we can verify it, but I still have to prove it to you. Just because I claim it doesn't make it true. So let's check. Okay, well, how would I do it? Just plug this in to the equation and see if it works. So I'm just going to work out what I get if I multiply x naught bar on the left by AB. And if I end up getting the zero matrix on the right hand side, well, then that means this worked. Okay, well, how are we going to work this out? I don't know what anything is, right? All I have to take advantage of is properties of matrix multiplication. So the first thing I'm going to do is use the associative property to switch the brackets around a bit and write this as A times B x naught bar. Okay, well, by assumption, this is equal to 0, because remember we assumed that x naught bar is a solution to this system here, this matrix equation. So, and just to clarify, to emphasize that, this statement is really just saying we really just assumed that bx naught is equal to 0. That's really what this line really means. I'll just underline it in green to make it clear. That's what this really means. This is what we assumed. So, well, then that means this is equal to B. Or pardon me, this is equal to the 0 matrix, right? So this is equal to A times the 0 matrix. And A times anything times the 0 matrix is just going to be the 0 matrix. So that's how we get the 0 that we were looking for over here. So now that verifies this claim. X naught is also a solution to this matrix equation. But this is the associated homogeneous system to the product matrix A to B, AB, which we assumed was invertible. And if the matrix AB is invertible, that means that this matrix equation has only the trivial solution. Again, we're taking advantage of the equivalence of 1 and 2 here. Okay, so let's write this. Since AB is invertible, the matrix equation AB x bar equals 0, this has only the trivial solution. And therefore, we can say that this x bar naught is really the trivial solution. Because if we verified that this x naught bar is a solution to this matrix equation, which based on the fundamental theorem of invertible matrices, this only has the trivial solution. Well, that means this must be the trivial solution. So that's what we've kind of written down here. But now, if you were to bundle this portion of the work all up in one chunk of work, what this really shows is that bx equals 0 only has the trivial solution. Because let's look at how this went. First of all, we started by assuming we had some solution. I should have the word 2 here. Suppose that x naught bar is a solution to the matrix equation bx equals 0. Okay, well, it followed from our work afterwards, we were able to conclude, therefore, that this x naught bar is actually equal to the trivial solution. Well, that means that this only has the trivial solution. That means the matrix equation bx equals 0, the associated homogeneous system with the matrix B, has only the trivial solution. Well, again, based on the equivalence of statement 1 and statement 2, that means the matrix B is invertible. So now we can conclude, based on this work here, therefore, B is invertible. And you might think, well, we can just do the same argument now for A and kind of do the exact same thing to conclude that A is invertible. But unfortunately, this strategy only worked because B was the factor on the right of this product. And really, it comes down to this part here. The fact that we could shuffle these brackets. If you had a solution attached to AB, you could just shuffle the brackets over and attach that solution to B, really. This step really took advantage of the fact that B was the factor on the right. So we can't just do the same steps to show that A is invertible. And we're still not done until we can show that both A and B are invertible. So here's how we'll finish this off. It actually turns out to be easier. Now that you know that B is invertible, because one of the things that we said about invertible matrices is that their inverses are also invertible, right? And because of that, the rest of this won't be very hard. So since A, I'm going to write it as a very specific product. I can write this as the product of AB and B inverse. So now the product A and B here, AB, was assumed to be invertible in the question, right? We started with the assumption that we had matrices A and B such that the product AB is invertible. That was an assumption. Now B inverse, well, we've already shown that B is invertible, so its inverse is also invertible. So in other words, A is the product of two invertible matrices. So since A is the product of two invertible matrices, A is also invertible. Okay, and that's all we need. So that is the end of the proof, because we've shown that both A and B are invertible. So compare that to a related but not quite the same statement. This statement says that if A and B are square matrices such that you know in advance that the product is invertible, this statement just says that the only way that can happen is if both A and B are invertible, and that's what we just proved true. So in other words, you're not ever going to multiply two matrices that aren't invertible and somehow get a product that is invertible. That just never happens, which is what we've proved. Now, that's not the same as a statement that we have seen before already and also proved, which is that if you start with two matrices in advance that you know are invertible, then their product is going to be invertible. That's a different statement, and it's one we've already proven. And in fact, it's one we took advantage of in the last part of this argument.